In this video, we are going to learn how to draw shear force diagram and bending moment diagram for a cantilever beam subjected to gradually varying load as shown in figure. The gradually varying load is a type of load which starts with a load of zero intensity at one end and varies linearly to the other end of beam. The gradually varying load is also known as uniformly varying load or triangular load. So in today's lecture, we will solve a numerical problem based on this type of loading. So this is the cantilever beam AB of length 3 meter which carries gradually varying load which has load 0 kN per meter at fixed end, and it increases gradually up to load 2 kN per meter at the free end of cantilever beam. So for this setup, we have to draw the shear force diagram and bending moment diagram. So first of all, I will draw the free body diagram for this beam section. So for solving this numerical problem, first we have to convert this gradually varying load into point load, whose value will be equal to the area of this triangle. So the point load equal to area of this triangle, that is 1 by 2 base into height, where base of this triangle is 3 meter and height of this triangle is 2 kN per meter. So it will get the point load of 3 kN. Now this converted point load will be acting at the centroid of this triangle. So the centroid of this triangle will be at a distance of 2 by 3 of the total length of beam from left end, or 1 by 3 of the total length of beam from the right end, that is 2 by 3 of length 3 meter from left end, or 1 by 3 of length 3 meter from the right end. So this converted point load is acting at this point. Now this type of problem we are going to solve in 3 steps. In the first step, we have to calculate the value of support reaction force RA. So to calculate this value, I will use the condition of equilibrium, that is summation Fy equal to 0. That means addition of all forces in the vertical axis equal to 0. While doing the addition of all vertical forces, I will consider upward forces as positive and downward forces as negative. Here RA is the vertical reaction force acting on the beam in the upward direction. So I will add this force with positive sign, and the converted point load of 3 kN force is acting on the beam in the downward direction. So I will add this 3 kN force with negative sign. So from this, I will get the value of reaction force RA equal to 3 kN. So now with the help of this calculated value of RA, I will further calculate the values of shear forces at all the points of beam. So the next step is calculations of shear forces. So here the sign convention for shear force calculation is upward forces are considered as positive and downward forces are considered as negative. Here you should remember that while calculating the shear force at a particular point load, you can calculate the shear force values for left side and right side of that particular point load. But while calculating the shear force at a uniformly varying load, you should calculate shear force values at start point and end point of uniformly varying load. That is shear force at point A and shear force at point B we need to calculate. But in this diagram, at point A, the reaction force is acting on the beam, and since this reaction force is a point load, hence we have to calculate the shear force values at left side and right side of point A. So here I will start the shear force calculation from left side of point A, that is SF at A to the left. So as you can see, there is no force is acting at the left side of point A. Therefore, SF at A to the left equal to 0. So to draw shear force diagram, I will first draw a horizontal reference line of 0 kN shear force. So here I'll mark the point of 0 kN. Now, when we move towards the right side of point A, that is SF at A to the right, then there is reaction force RA which is acting on the beam in the upward direction. So as per the sign convention, I will consider upward force as positive. So here the shear force is plus 3 kN. Here as the shear force value is positive, so I will mark the point of 3 kN shear force above the reference line of 0 kN shear force. And I will connect these 2 points with a vertical line. Now point B is the end point of uniformly varying load. So I am taking section to point B and I will calculate the shear force at point B, that is SF at point B. And here I'll carry forward previous value of shear force up to point A to its right, which is 3 kN. And to the left side of point B, there is gradually varying load that we had converted into point load of 3 kN, which is acting on the beam in the downward direction. So as per the sign convention, I will consider this downward force as negative. So I will add this point load of minus 3 kN. So here plus 3 kN minus 3 kN gives me the value of shear force at 0 kN. So I will mark this point of 0 kN shear force at point B. And here if you can see, between point A and point B, there is gradually varying load. And to draw the shear force, I will indicate gradually varying load with a parabolic curve. So I will connect these 2 points with a parabolic curve. And here in shear force diagram, whatever the portion drawn above the reference line, I will show this portion by plus sign. So here I have completed the shear force diagram. Now the next step is calculations of bending moment. So bending moment at a section of beam is calculated as the algebraic sum of moment of all the forces acting on one side of the section. So to calculate bending moments, we can start either from left end of beam or from right end of beam. So here I will start from right side. So whenever you are calculating the bending moments, you should remember these conditions. So here for cantilever beam, the condition is at the free end of cantilever beam, the bending moment will be 0. That is Bm suffix p equal to 0 kN meter. So to draw bending moment diagram, firstly I will draw the reference line of bending moment 0 kN meter. So I will mark this value with a point on the reference line. So now we have to calculate bending moment at point A. So here, in case of cantilever beam, while you are doing the calculation for bending moment at a particular point, you should always add moment of all the forces present from the free end of cantilever beam up to that particular point at which you are calculating the bending moment. It means, while I am calculating the bending moment at point A, I will add moment of all the forces present from the free end of cantilever beam up to point A. And for bending moment calculation, our sign convention is, for sagging effect of beam, the force is considered as positive, and for hogging effect of beam, the force is considered as negative. So the bending moment at point A, that is Bm suffix A, equal to algebraic sum of moment of all the forces at right hand side of point A. So here at right hand side of point A, there is gradually varying load, that is triangular load, which we had converted into point load of 3 kN, which is acting on the beam in the downward direction. Due to this downward force, the beam shows hogging effect, and for hogging effect of beam, I will consider this converted force as negative. Hence the amount of force is minus 3 kN into distance from point of action of force, that is 2 by 3 of length of beam, that is 2 by 3 into 3 meter. Therefore, after calculating this, we will get the value minus 6 kN meter. So as it is negative value of bending moment. Hence I will mark the point of bending moment below the reference line of 0 kN bending moment. And here if you can see, between point A and point B, there is gradually varying load. And to draw bending moment diagram, I will indicate gradually varying load with a cubic curve. Hence I will join these 2 points with a cubic curve. And I will connect these 2 points with a vertical line. Now since I can see this bending moment diagram is drawn below the reference line of 0 kN bending moment, hence I will show this portion by minus sign. So here we have completed the shear force diagram and bending moment diagram for this cantilever beam.